Hi everyone, my name is Krisha Patel.
I'm Aarushi Gupta.
I'm Michael Fang.
I'm Grace Clemen.
And I'm Letchuman.
Before we begin discussing the open cluster we researched, to start off, what is an open cluster? Held together by stars, open clusters are groups of stars with similar ages, compositions, and distances from Earth. These clusters develop when molecular clouds collapse, and there are thousands of stars in the cluster that are all extremely active. And this image on the slide is one example of an open cluster. Open clusters are essential for understanding star evolution because there are many relatively young stars. Stars from open clusters also form one giant molecular cloud, and since they have similar ages and compositions, it is easier for astronomers to determine properties using photometry, which we also use in our own research as well. Overall, open clusters aid in identifying the effects of variables on stellar properties and stellar evolutions.
The open cluster our project is focused on is NGC 1245, which was first discovered by William Herschel in 1786 and was previously studied back in 1964. NGC 1245 is part of the constellation Perseus and has over 500 members, in which our project culminates 461 of them. The data for this cluster was provided by the Roque de Muchachos Observatory of the Southeastern Association for Research in Astronomy, also known as SARA. Our targets for this project were divided into two categories, scientific and group goals. Our main scientific goal was to determine the age and distance to the open cluster NGC 1245, and our group goal was to collectively interpret a large data set of stellar magnitudes in both the blue and visual filters using AstroImageJ software. The outline of our project is divided into 5 main steps: determining the star numbering system and star division, photometry on AstroImageJ, correct values to account for reddening, graphing the data set to determine the turnoff point, to finally determine the age and distance.
So before we could do anything, we needed to determine a star numbering system to organize and identify stars, because as you can see, there's over 500 stars in NGC 1245, and we needed a way to organize them so we could know which star is which. And what we eventually did is we looked through a few star numbering systems, and we settled on one made by Guido Scincarini, who is an Italian astronomer. And you can see his star numbering system here, the one we used. Yeah, so next, photometry. Photometry is basically what we did our entire internship. It's the science of measuring light in relation to a observed brightness as opposed to the actual brightness of the star. So we used AstroImageJ, which is an astronomical image analysis software, to determine the magnitudes of target stars in NGC 1245 in relation to B and V filters. The magnitude of target stars is just their brightness. It's a measure of brightness, and we took their apparent magnitude, which is the measure from a human eye or from like a telescope from Earth. And B and V filters are filters which are used in astronomy to improve contrast and make it easier to analyze like images like this by removing clutter from images. And they work by only allowing specific wavelengths of light to be observed. And so the B filter is a blue filter, and it only allows light of wavelengths 400 to 500 nanometers through. And the V filter is visual and allows light wavelengths 500 to 700 nanometers through. And these apparent magnitude measurements are all taken in relation to a reference star. As you can see below, this is the formula to get the magnitude of a star. And to get it, you need to know the magnitude of another star, which is a reference star. And we selected star 125 from Scincarini's star numbering system as a reference star because we know its magnitude. And using its magnitude, we can calculate the magnitude of all the other stars in NGC 1245. So reddening is, or redshift, it's an astronomical phenomenon, and it happens to all astronomical data ever. And it's basically when light from a star interacts with interstellar particles, the wavelength of the light is stretched and the color is shifted towards the red end of the visible spectrum. And what this does is it basically just has all the observed light from space be a little redder than it actually is. And we can correct for this by calculating and determining a reddening value, which is like how much redder it gets, and subtracting it from its measured value to get its real value.
So this is our graph. On the x-axis, we have the color index, or the B minus V, and on the y-axis, we have the V values. And so underneath it, we also have the ZAMS line, or the zero-age main sequence line, which represents the time when stars initially enter the main sequence on the HR diagram. So what we are looking for is a cutoff star, because an open cluster can be no older than its youngest star. So we have to base off all our calculations off of the cutoff star, which we determined to be star 422. And so for our calculations, we have to find in absolute magnitude, and we can't tell that but based off of our data. So we have to find a star that has a very similar B minus V to our cutoff star and use that absolute magnitude. So we decided on a reference star of HIP 111.807 with an absolute magnitude of 2.13, and its cutoff star number is 422, and with the parent magnitude of the cutoff star being 14.05. And so plugging it into the distance formula, we get 2,856.27 parsecs, which is equivalent to 9,311.46 light years. And so to determine the age of the open cluster, we have to use spectral class. And basically, it's based off of the stars B minus V values. We can sort them into the spectral class. And based off of that, we can find their age, color, size, and temperature. And for the purposes of our experiment, we wanted to find the ages. And our cutoff star, happened to be an A star. So based off of the fact that it's an A star, specifically an A5 star, we can determine that our globular, or our open cluster, is approximately 1 billion years old, and the distance from it is 9,311.46 light years.
So the first thing we learned is we learned exactly what open clusters were in astronomy. And the next thing, we learned how to use astronomical software like AstroImageJ. So ImageJ, many of y'all will know, is extensively used biomedical software. And AstroImageJ was very useful in our project in finding photometry, like Michael discussed, of these stars in NGC 1245. Now, the third thing is we learned how to interpret large data sets. The five of us interpreted of over 400 stars, and we corrected for reddening. We graphed these scatter points, and collaborated with like-minded students, and we also received the opportunity to work with an amazing professor. And Miss Kuper is a PhD student. She works at Caltech. She's also worked in high school, and she's an amazing mentor. And the last thing is we gained career experience. Many of us have sort of honed in our decision on whether or not we're going to pursue a career in astronomy, and NASA has definitely helped us make that decision. Some of the challenges we had were, it was really unclear about these large groups of stars. These stars in our images were in groups, and many of them were very faint. And it was hard to distinguish between them. So these stars had such low magnitudes, and it really made us have a difficult time finding the magnitudes and to get sort of precision in that process. Second challenge is the virtual communication and collaboration. We did everything over Zoom. We did everything over text messages and phone calls. So of course, we had to deal with that. It wasn't in person. And the last thing is an interesting challenge. Our data was supposed to fit a certain line. It's called the main sequence line of zero-age main sequence. But our scatter points didn't really line up with that line. And we had to do some adjusting to make sure that those scatter plots were on that zero-age main sequence line. And once that was the case, our data was able to be interpreted.
To begin, working on this project gave me the opportunity to explore new topics in astronomy and the experience of collecting large amounts of data, which I have not done before. And especially, I'm super thankful to NASA Seas and our mentor, Ms. Kuper, for giving me this chance and also guiding me throughout our journey of our research.
Being given a chance to do this project has given me unequivocal inspiration and excitement to go into a career in astronomy, because I've loved to learn about the theory, but I've never actually gotten the chance to actually collect data and interpret it. And so that was an amazing experience. I'm so happy I got to do a project like this, and I can't be more grateful for SEAS for the opportunity.
Yeah, I want to thank C's and Miss Cooper for this amazing experience. And I really loved doing all the actual like astronomical work that NASA does, like getting a taste of it. And I'm gonna remember this going forward, and I hope I can do more in the future because this was my first like actual experience in astronomical research.
Yeah, so C's really helped me enhance my understanding and solidify my interest within space science. And I really had the grateful opportunity to engage in astronomy through the scientific lens, and am thankful for C's for the experience that I've had over these past few weeks.
And like I say in this statement here, before I attended SEAS, I had done a bunch of research in astronomy. I attended lectures, I'd taken images in my telescope and such, but I never had that true, authentic, and genuine research experiments with astronomy. And I will never forget how invaluable NASA SEAS has been in providing me with such a strong foundation in astronomical research. So thank you so much, NASA SEAS. And on behalf of all of us, we would like to thank NASA. We would like to thank the Texas Space Grant Consortium, the NASA SEAS program, as well as the Center for Space Research Science in UT Austin. UT Austin was very kind to include us in this program. And of course, we'd like to thank our mentor, Mrs. Kuper. She's been an amazing mentor. And we'd also like to thank all the coordinators of the SEAS program. Thank you so much.